This video is about simplifying radicals. There are two things we want to be able to do to simplify radicals. One is to simplify a radical such as the square root of 50, which is not a perfect square. And the second is to be able to add and subtract like radicals, which we'll get to in just a moment. So we already know that the square root of 50 is not a perfect square. But we also know that 50 is 25 times 2. And we have a rule that says if I have the square root of a product, a times b, that I can take the square root of a times the square root of b, provided a and b are both positive numbers. So for the square root of 25 times the square root of 2, we could take the square root of 25 times the square root of 2, and our result would be 5 radical 2. Here's another example. The square root of 500 we might write as 100 times 5. Then we could take the square root of 100 separate from the square root of 5. The square root of 100 is 10, and we cannot take the square root of 5. How does this work with variables? Well, the square root of x squared is x, because x times itself will give us x squared. If I had something like x to the 6th, I might think of this as x squared times x squared times x squared. And then I could take the square root of each piece separately, leaving me with x cubed. So one thing we can think about, we don't really see this square root symbol, but what we're doing here is we're dividing 2 into 6, and we know that 2 goes into 6 3 times. So what happens if it's not an even number? What if I have the square root of y to the 7th? Well, that would be y squared, y squared, y squared. That's 6 y's, and one more would give me 7 y's. Well, I can take the square root of each of these y squares, 1, 2, 3 of them, but I'm still left with 1y underneath. So you might think of this as saying 7 divided by 3 is, let's go back. 7 divided by 2, my index, is 3, with a remainder of 1. Here's another example. The square root of x to the 4th, z to the 17th. So again, our index is 2. 2 goes into the 4 2 times, so we'll get x squared with nothing left over. I call this my leftover pile. And 2 goes into 17 8 times. That gives us 16 with 1 left over. When we add and subtract like radicals, it's very much like adding and subtracting like terms. So if I have 3 radical 5 plus 9 radical 5, I'm going to get 12 radical 5. So I'm just adding these numbers here. When I have, for example, 3 radical 2 plus 5 radical 6 minus 7 radical 6, the only two that are like radicals are 5 radical 6 minus 7 radical 6. So I can only add those two and get 3 radical 2 minus 2 radical 6. If I have, for example, minus 5 radical 2 plus 3 radical 18, they really don't appear to be like radicals. However, 18 is 9 times 2, and 9 is a perfect square. So we're going to rewrite this as minus 5 radical 2 plus, I'm going to take my 3 out of the radical, and I'm going to multiply it by that 3 outside. So I'm going to get 9 radical 2. So what happened there is I took the square root of 9, which is 3, and I multiplied it by that 3 that was out in front. So now I have two like radicals. Minus 5 radical 2 plus 9 radical 2 is 4 radical 2. Let's look at a couple of additional examples. Let's do the square root of 300 x cubed minus x times the square root of 12x. Now remember, I want to break up my radicals using perfect squares if I can. So I'm hoping you can see that this 300 could be written as 100 times 3. Because 100 is a perfect square. Now I could break up 12 as 6 times 2, but neither one of those is a perfect square, so I'm better off to think of it as 4 times 3, because 4 is a perfect square. So I'm going to take these perfect squares out. The square root of 100 is 10. I cannot take the square root of 3. When I do the x's, I'm going to divide. 2 into 3 goes in one time with 1 left over. Here I'm going to take the square root of 4, which is 2. There's the x that was in front, times the square root of 3x. And these are like terms. 10x radical 3x minus 2x radical 3x is 8x radical 3x. For the last example, let's do a cube root. Let's do the cube root of 16 plus 5 times the cube root of 54. Now it's helpful here if we know what the perfect cubes are. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. So when I think of 16 and it's a cube root, I want to say, is 16 divisible by any of these numbers here? And I hope you can see that 16 is 8 times 2. Same thing with 54. 54 happens to be 27 times 2. So I can actually take the cube root of 8, which is 2, leaving the cube root of 2. The cube root of 27 is 3, but when I pull that 3 out, I'm going to multiply it by that 15. And I'm going to end up with 17 cube roots of 2.